This is the fourth session of our Climate Café, and our guest today is Dr. Joyce Penner. This Climate Café session dives into the fascinating world of the atmosphere and its connection to a warming planet. We'll explore the science of the greenhouse effect, understand how human activities are affecting this delicate balance, and delve into the science behind radiative forcing. We'll also take a closer look at the troposphere, the layer of air closest to us, and its chemical composition. Finally, we'll explore the pressing issue of aviation emissions and why pollution at high altitudes can have a more significant impact on climate change. Join us for an engaging conversation where you'll learn how the atmosphere functions, how human activities are influencing it, and gain insights into the challenges and potential solutions to high altitude emissions. And our very first question is, what is the greenhouse gas effect, and what does it look like in the atmospheric level?
The greenhouse effect is due to infrared radiation, so radiation between 10 and 14 microns or so. And it is, all matter emits radiation, right? And the amount of radiation depends on the temperature. So, and that determines the wavelength. So infrared radiation comes from the surface of the Earth, originates from the surface of the Earth, and it's captured within the atmosphere by greenhouse gases. So they don't let all of that radiation from the surface get out to the to outer space. They trap it and send some of it back down to the Earth, and that ends up heating the Earth more. That's basics of greenhouse effects.
Got it. So following up on this, what is radiative forcing?
So radiative forcing is kind of defined in a special way. It is, as forcing by greenhouse gases occurs, the temperature is changing and keeping up with that forcing. But what radiative forcing is a measurement of the outgoing radiation, or actually it's the incoming radiation, at the top of the atmosphere before any changes in the temperature take place. So it kind of tells you a potential for how much effect you'll get from different greenhouse gases, or in my study, it's how much effect you get from aerosol particles.
All right. Crucial, I think you're up for the next question.
Our next question for you is, what is the troposphere and why is it so important when we discuss climate change?
Well, the troposphere is where most of the weather takes place. The temperature is mainly decreasing with altitude from the surface to the tropopause, and then it increases in the stratosphere. And what that means is most of the water vapor is trapped within the troposphere. Water vapor, of course, is a very important greenhouse gas, and it's a natural greenhouse gas, of course. So it's important because of the weather and the fact that that is the part of the atmosphere that affects us as humans living on Earth the most.
Following up on that, why are gas and aerosol interactions important for climate models?
Well, aerosols, unlike greenhouse gases, mainly reflect incoming radiation, so solar radiation as opposed to infrared radiation. And that means that they also affect climate. But mostly in an opposite manner to greenhouse gases. And I don't know, did that answer the question?
I
Yeah,
think we
good.
might need, I think I might need a little bit more clarification.
So ask the question again.
Right. I think he asked, why are gas aerosol interactions important for climate models?
So you're talking about the interaction between gases and the aerosols.
Yes.
The main interaction is that of water vapor, because the aerosols are made up of materials that take up water. And so that grows the size of the aerosols. It makes them primarily more reflective of the solar radiation. And it determines which of the aerosols are able to grow so large that they form a drop. The drops, if they get large enough, can then form precipitation. And so aerosols and aerosol gas interactions in that way really control where a lot of the precipitation occurs.
Okay. Well, that makes quite a bit of sense. Is this also relevant when we talk about some other greenhouse gases that are found as aerosols? I think when we think about the Montreal Protocol, a lot of those hydrofluorocarbons, they're quite small, aren't they? The refrigerant particles, from what I know.
So the refrigerants are mainly gases, but they are oxidized in the stratosphere. They form compounds which can interact with the aerosols, so not water like I was talking about in the troposphere, but and they, and especially at cold places like over the poles, they form particles there, and those particles interact to destroy ozone. That's why we have the ozone holes over the poles.
Right, okay. So we're talking about interactions at different levels of the atmosphere. So water vapor is kind of more the troposphere, and when we talk about like fluorinated carbon compounds, they're in the stratosphere. Is that correct? All right.
Yeah, they're long-lived
Okay.
primarily, and so they're destroyed in the stratosphere.
All right, got it. Our next question is, how do pollutants from biomass burning and fossil fuels affect the formation, the size, and the lifetime of aerosols? And in turn, how do these aerosols influence cloud properties?
Fossil fuels for sure have a lot of sulfur contained in them. So as they oxidize in the atmosphere, the sulfur oxidizes, and that is able to form sometimes new particles. So, and sometimes just deposits on particles that are already there. But that is extremely important in terms of because sulfate is able to take up water and grow water on its surface. It's primarily involved in interactions with low clouds and the formation of those low clouds. Biomass aerosols are primarily soot and organic carbon. They also have some sulfur. And some work I've been doing seems to indicate that even the amount of sulfur is not that important. Even a small amount of sulfur can, enhance the formation of droplet numbers. So the organic and carbon and soot particles from biomass burning can also be cloud condensation nuclei. And yeah, and also not very well known is whether the particles of different composition are able to form cirrus clouds, so ice particles, which gets into the issue of, what happens with aircraft emissions.
Mm-hmm. Mm-hmm. Just another follow-up question before we go into the topic of aviation emissions. So what you've spoken about, does it have any ramifications to the water cycle? Like, does it speed up the rate of precipitation or?
So the rate of precipitation is primarily determined by the surface temperature, right?
Mhm.
So the rate of evaporation, I'm sorry, is primarily determined by the surface temperature. And as the atmosphere warms, you can have more water vapor in the atmosphere itself. But if you look at the globe as a whole, precipitation and evaporation are pretty balanced. So the aerosol particles can affect where the precipitation takes place, but not so much the total. They aren't as important in terms of the total precipitation. If
Mhm.
if you start looking at regional scales, they make a
Mhm.
difference for sure.
Mhm. Mhm. All right, that makes sense. Yeah. I think Rachel's got the next question.
So as we were going into aviation emissions before, why do you think aviation emissions seem to have a bigger impact on climate change compared to emissions on the ground?
Oh, I don't think they have a bigger impact. The especially if we're talking about cloud interactions of the aerosol particles, the low level clouds are reflecting a lot of information of shortwave radiation. So small changes can have a major impact. The cirrus clouds don't reflect that much. And cirrus clouds are also trapping the infrared radiation. So I don't think there's a bigger effect, but I think it's an important effect.
Mhm.
And there's still a lot of uncertainty in terms of what it is that forms those clouds without aircraft. And then if you add aircraft, how is that going to change? And yeah, so there's all those issues.
Mhm.
And aircraft emissions not only include the aerosols, but they include gases like NOx as well as CO2. And the industry is concerned about whether effects, how those effects balance out.
Mhm.
So cirrus or contrails that form behind aircraft are, I think, almost larger in terms of the radiative forcing than CO2.
Mhm.
So
Mhm.
some of the aircraft companies are studying how to avoid making contrails.
Mhm. Mhm.
Interesting. Do you think the volume of emissions make a difference in aviation versus on the ground, or is there not that big of a difference?
Oh man, there's a lot more surface emissions than those at aircraft altitudes. What's unique about the aircraft is it's at altitude. So it's being put into a place in the atmosphere where cirrus clouds can be affected.
Mhm.
And then there's, a lot of uncertainty about how those cirrus clouds are affected. There's not, to my knowledge, a lot of uncertainty in terms of contrail formation and why that happens and where it happens, except if you're thinking about building aircraft that do not emit soot particles, but do emit volatile particles. And the question is, would those volatile particles form contrails in the same way as the soot particles? Or how are they different?
I wanted to ask, sorry, Rochelle, I'm going to cut you, but
Absolutely.
I wanted to ask a question because I read parts of the report that you authored for the IPCC on aviation emissions, almost 25 years ago. I noticed that when I saw the calculations for aviation emissions, it seemed to have a higher amount of radiative forcing. And I guess that's what prompted my question about asking whether it was more dangerous than emissions that are done on the surface. So my question is, why do we calculate like emissions from airplanes at an altitude with a higher radiative forcing?
You mean if it were the same total emissions, the
Yes.
radiative forcing from high altitude would be larger than from the surface. There's a number of factors that go into that. One is the fact that a surface emission encounters rising air parcels, which form clouds, which then precipitate and remove those particles, whereas at altitude, that doesn't happen as quickly. So aerosol particles emitted from the surface might have a lifetime of 5 to 7 days, whereas aerosol particles emitted at altitude have a 25-day lifetime. So, you don't have to emit as many particles to have a larger effect.
Right. Okay, that makes sense.
Interesting. So following up on that, do you think, therefore, is cutting down on flying the best way to minimize our personal carbon footprints?
Well, if we're talking about right now, I certainly have been trying to avoid flying. So I'd much rather go to meetings via Zoom than to actually have to travel there by airplane. And although there's a lot to be gained, I must say, by being able to go to a meeting in person. But I think it's more a question of, in terms of decreasing emissions, figuring out what the best way to do that is, doing that together with the industry so that a solution that is viable for that industry is able to be figured out. So, people have talked about using biofuels, but using biofuels may not decrease soot emissions as much as you might want. And for cirrus clouds or contrails in particular, the idea of being able to predict where a contrail would form. So that depends on regions of supersaturation in the atmosphere. And then if you can predict that, you can have the aircraft fly around that area, avoid it. That'll cost more in terms of the CO2 emissions, right? So that's all a very active research area. In fact, the National Academy of Sciences is doing a study now to inform NASA what kind of research needs to be done to improve our ability to not form contrails.
So what I'm getting from that is that your opinion is the burden doesn't just fall on individuals, but also on the industry.
Yeah, oh yeah, they're already involved, which I had not realized, but they are doing experiments with different companies. I think Google is involved to try to figure out if they avoid certain regions, whether contrails in fact are decreased and how to do that. What I've learned in one of the meetings was the weather models that are predicting areas of supersaturation. The Germans have done experiments where they know if they avoid these regions with high supersaturations, they cannot, avoid forming contrails. But the ability of the weather models to predict those regions is it's restricted to very, very large and intense supersaturation regions. So, maybe 60% or so of the regions that are supersaturated are actually be able to be predicted. So there's a question of how efficient is that going to be? What the trade-off with CO2 emissions is, and as well as other emissions like NOx and yeah.
Passing that back over to Tanvi.
Yeah, I wanted to say we actually discussed the paper that you were talking about, the one that Google did about how aircrafts can kind of, I guess, change their route a little bit in order to prevent the formation of contrails. And it spurred a little bit of a debate in our group, actually, because we were wondering if we're assuming that a typical flight path is, the shortest distance, so a straight line, if it does have to deviate in order to prevent the formation of contrails, would that lead to more carbon emissions if we're assuming that it flies a longer path? Do you think that's something to worry about, or?
Yeah, no, it definitely leads to more emissions of CO2.
Okay.
And then the question is, does that end up overtaking the amount of radiative forcing that you would just get from the contrails that form?
Mm-hmm. Yeah. Well, I guess that's over for the people at Google to figure out. Our last question for you is not a very scientific one, but what piece of advice would you give young people who want to go into studying fundamental climate science?
Well, your education is terribly important. And it's a very, very broad education that includes not just atmospheric science, but mathematics and statistics. And if you're going into the areas involving chemistry, that's also very important. So education is very important. I think building your career after you get a PhD by giving, as many papers at conferences as you can and trying to meet other atmospheric scientists who are your age, as well as more established atmospheric scientists, can be extremely helpful. I know there's a lot of early career events that take place at conferences, and that's probably useful to go to those. I don't know what else. Be sure for anything to get into answering questions that you find important. It really, it takes a lot of effort, usually, to work through a problem. I know for myself, I'm trying to do machine learning things now, and it's not easy to find the answer that I expected. And so there's, but being persistent and having a lot of curiosity about the phenomena that you are studying is very important to keep you going, for one thing. Yeah. So
I think
I
that's
don't know
great
if
advice. I have one question. Now we're done with our official question. So if anybody would like to ask a question, you can raise your hand and I'll let you go after me. I have a question. In a lot of your answers, you spoke a lot about a sort of inherent uncertainty in climate science. And I want to talk to you about that because I'm very new to the topic of uncertainty in climate science because for so long, the fundamentals of it seemed like a bedrock. And then I started studying climate models and I'm like, whoa, we don't know a lot. We don't know how clouds work. We don't know, I'm reading new papers almost every week in Nature about, different processes in the deep sea that affect how ocean and CO2 circulate. As a climate scientist, especially one like you who's been in the field for so long, how do you get comfortable with this complexity and uncertainty? How do you deal with it?
Well, there is uncertainty related to the specific issue that you're working on, right? And that requires, in my field of aerosol particles, requires specific knowledge and knowledge about how well various factors that go into whatever affect your computing, what those factors are and how they sum together to make an entire amount of uncertainty. In a broader climate sense, like oceans, I don't study oceans, so I have to rely on, reports like IPCC reports to tell me what the fundamental uncertainties of those aspects are. And I know I've often had a lot of curiosity about climate sensitivity. What is it? Different models get different answers. And, like when I go to an AGU meeting, I go to a lot of the sessions on climate sensitivity because I'm just very, very interested. Not that I do work in that area, but I see over time progress being made. Bringing together different fields to try to answer questions like that, like paleoclimate, as well as current climate models, and and in the last several years, people have done research into clouds that form in the Southern Ocean, and when they've tweaked their climate models to fit those observations, then they get more uncertainty and even higher rates of climate sensitivity. So that's not something I understand particularly, but I understand the fundamentals of how climate sensitivity depends on the response of climate models in terms of how much cloud is formed as the climate warms and that sort of aspect. So I don't know, did that answer what you needed?
Yes, no, it did. Yeah, it makes sense. Does anybody else here want to ask a question?
I actually did have a question. As an engineer, I'm like primed and taught to consider all different parts of the system, including like the fact that I pursue an economics minor, I consider that. I pursue an engineering major, I consider the technology behind it. And now I'm interested in climate science, so I now consider that. How do you, how would, in your career, how have you gone about kind of bringing everything together, working with different people to try and understand from a systems perspective what your research implies on different areas of our society?
I think I've relied on other people in the field that were more knowledgeable than I am. Like this climate sensitivity issue, one of the early papers I wrote on aerosols and their impacts on climate, used a model that turned out to have much higher climate sensitivity than other models. I couldn't explain that in the paper. I had to have a co-author who understood that field much better and who could argue with referees who said, yeah, no, this can't be right. And so I think working with co-authors is a good way to establish yourself in areas that you don't know initially, and then you can go into those. Another tactic I used was to not go after the biggest problem in a new area, but go after a substantial problem that was doable for me. I remember using just a parcel model that follows a parcel up in the atmosphere and then forms a cloud, and using that to study a problem with respect to how aerosols affect clouds. And that, that was not a terribly big problem, but it was important to me in terms of establishing to the rest of the field my expertise in being able to do this kind of research. And then you can expand out a little bit more. That's the way I think about it anyway.
Makes complete sense. Thank you so much.
All right, we have a question from Shurabi Mercado. Would you like to ask her yourself? I think you can unmute yourself. All right, if not, I'll ask
Hi,
her. Okay,
am
you
I
got it.
audible? Sorry.
Yes, we can hear you.
Yes. Okay, perfect. Hi, it's really nice to meet everyone and especially you, Dr. Penner. So hi, just a little bit of a context. I just graduated from biotechnology engineering, specializing myself in environmental science and bioremediation. But I'm really interested in all climate models and different analysis, and this has been really insightful. But my question is more regarding the complexity of these topics. Now, these can be really focused, specialized fields that maybe many times very technical or complex. So how can we better communicate these results, these data, in a way that we're not just informing them, the population in an easier way, but how can we actually get the work that we're doing, get the research, get everything so that we can influence governments and influence policy?
Boy, influencing policy. As somebody who kind of saw, I've seen the community asking for mitigation of greenhouse gases for, 30, 40 years. And it's just now happening. And being part of IPCC, which is really a way to inform policymakers of where the science is. So I think it's very hard to influence policy because there's all kinds of other things. I mean, I remember at one point thinking that, yes, they're finally going to pay attention. And then a worldwide recession took place, and the policymakers wanted to worry about economics, not about climate. And yeah, so that's not easy, but writing papers that are relevant to policy from an atmospheric science perspective, which was my perspective, it means that institutions like IPCC will be aware of what you're doing and then be aware of bringing that forward if it's, depending on the importance of the issue, to policymakers. And that's, as a scientist, that's how I would look towards trying to influence policy.
All right, I hope that answered your question. All right, she says, thank you. Well, that is all the time we have today. Thank you so much, Dr. Penner, for coming on Climate Cafe and answering our very many questions. I think a lot of us are very nervous as we foray into our careers, hopefully as climate scientists. And thank you so much for clearing up all of our questions about aviation emissions and the atmosphere. And we hope to maybe have you back someday when we have new questions. And yeah, thank you so much. Bye-bye.
Yeah, it's been a very major enjoyment for me. Thanks.
All right. Goodbye, everybody.